Okay, cool. Well, I'll go. I don't know who all is here. It looks like Rick and Carl are here. I don't know if Vlad and Vitalik are joining.
So Vlad is not going to be here. He's traveling, but he says hello to everyone. And I have an update kind of for Vlad through Vlad.
Oh, cool. Awesome. And I don't know about Vitalik. Hey, Carl. I'll give a quick update, and then I think Yoichi was going to join us too. He was having trouble on Skype. Let me just double check. Uh, 255-216-1381. Yoichi is having trouble.
So I got in through the last Zoom link, like last time. Not today, the one that was shared for last week.
Okay. Well, it's the same link. That's strange. All right, well, let's give Yoichi just another minute or two. Oh, okay, he joined. Okay, cool.
Yeah, thank you.
Oh, sure, no worries. Okay, I'll give a quick update and then hand it over to whoever wants to go next. So two things. Mostly I've just been dealing with the redemption process stuff. We have the rocks minted and all the backend scripts tested, and we had to redo some stuff on the front end as well for in order to work around some issues with deployment. That's all taken care of, so we are ready to run the AMP redemption, which is cool. But in addition, Mike, Stay, and I have needed to get some results down. So we're in the process of publishing those results. So the results have to do, in order to make our lives a little easier, we are dealing with, there's a relationship between monads and Levere theories. So the whole logic is distributive law, which is kind of the program that underlies what we're doing with the Rolang, is dependent upon a presentation of monads via Levere theories. And Levere theories don't deal well with nominal stuff. So by nominal stuff, I mean the message passing that you find in message passing calculi, like the pi calculus or the rho calculus. So it turns out that there are such things as nominal Levere theories. So what nominality really has to do with is fresh names. Being able to create fresh names and then make sure that you have all of the equations around when you create two names and they're bound to the same variable, what happens, and those kinds of things. So there are such things as nominal Levere theories, but we have a slightly different approach, which is less complex. So it turns out that you can give a completely name-free account of the rho calculus as follows. So first, you use Yoshida's approach to reduce the pi calculus or the rho calculus, either one, to prefix free. So prefix free means that instead of being blocked on IO, you have a bunch of combinators, which still, unlike the SKI combinators, which are totally variable free. Maybe take a step back. There's an algebra called SKI, which just uses those characters into which you can compile the lambda calculus, and that gets rid of abstraction. So Yoshida's approach is akin to the compilation of the lambda calculus to SKI. So it gets rid of prefix abstraction, but it doesn't get rid of new. So it still depends upon names. These are not entirely name-free combinators. So it still depends upon names, and it depends upon replication. So in the row calculus, you have reflection, which allows you to get rid of new. And the reflection also gets rid of replication. So by first applying her techniques to the row calculus to get rid of prefix, then you can essentially modify her combinators to include reflection, and then you get rid of new entirely. And as a result, we get a Levier theory that for the row calculus, which allows us to, apply the Ladle algorithm without having to fancy up the Levier theories that we're using. So we are publishing those results because we just need them out there because we depend upon those results. So I was in the midst over the last week of writing that all up with Mike and LaTeXing it. So we have a draft which will be going up on RChive in the next day or so and has been submitted to a conference. So let me just bring that. I'll just quickly do a screen share, and then I'll make sure that people have access to that. So here we go. Okay, yeah. So essentially, here's the paper, and I'll just do a very, very brief walk through. Hopefully that's big enough. Maybe I'll make it a little bigger. Okay. So just very, very briefly, not too much in detail, but so Yoshida's original combinator calculus has essentially combinators for the message. So you send B on A, you duplicate from A to B and C, you kill the channel A, so whatever you get on A goes to 0. You forward from A to B, branch right and branch left are a little bit complicated, but essentially it turns into a kind of forwarding, and then S distributes the name through similar to the S process in the SKI. And then in addition to these combinators, you can make fresh names, you can put processes in parallel, and you can replicate. So these have a notion of free name and bound name, and some rewrite rules that you add to the original PyCalculus rules. And that gives you a prefix-free calculus, and she has a little compiler, which is not so little, it's fairly complicated actually. There's the little compiler, which removes prefixes from PyCalculus processes. So by the time you finish running this on an asynchronous PyCalculus process, you get down to a process that only uses the combinators and new and parallel composition and replication. Now, it turns out that if you just add, so if you modify message so that it passes processes, and then you also have a combinator for reflection here, then you can get rid of everything. And so here's the new rewrite rules. And the basic idea is that when you have a channel A and it's a message on channel A of P, and it bumps up against reflected A, then you deposit P. So this is the little modification from Yoshida's combinators to get rid of the new and the replication. And then essentially here's the compilation. So first you do there's a little typo here, that should be 4. No, I got that right, never mind. So here's the little compilation from Yoshida's combinators, And then we have to swallow her prefix elimination equations, which is what I was LaTeXing up until 7:03 this morning. So we've submitted this to a conference, and a draft of the paper will be available on arXiv for people to review. And again, essentially, we need these are fairly technical results. We show then that you can give a presentation of all of this into graph enriched Levier theories, which allows us to it makes the technical basis for the application of the ladle algorithm a little bit cleaner, and also for some time having name-free combinators for concurrency was kind of the holy grail. I don't think people are as excited about that now, but it used to be a pretty hot topic, and this is a solution to that problem. So that's basically my update. Let me pass it over to whoever else has got an update.
So I'm finally here now, though I don't have to give extremely big updates to give. The biggest thing I've probably been working on from my side is continuing to write up that contract in Viper. So after some discussions with Carl, I think I've decided that it's best to just settle on an RLP format for the consensus messages, and I'm trying to figure out the kind of cleanest way to parse everything inside of the in EVM. So working on that, and looks like it's close to being ready. The other thing is that has Yuichi spoken yet about his verification stuff?
No, not yet.
Not yet. Okay, well, I'm starting to think more about the fork choice rule in the context of dynamic validator sets, and I haven't really gotten many results yet, but I'm starting to realize that there might be situations where he needs to be a bit more careful. So, like, one example is if you have a validator set and then you have some commits that change to another validator set, then what if the first validator set still makes another message? So, like, still signs a fork that's like way far in the future with the same validator set. So, like, without actually violating any slashing conditions. And basically, I'm wondering, like, can we deal with that either easily on the fork choice side or easily by like maybe adding an additional slashing condition? Looking at the fork choice side seems more reasonable, but it does mean that the fork choice rule have to be a bit more complex than I thought before. That's it from my side.
Oh, you reminded me, actually, I doing all this work on combinators made me realize that you can use a similar kind of source-to-source as a potential. So let me take a step back. Back in 2014, I took a look at doing a source-to-source translation from row calculus-based notion without gas to a row calculus with gas. And that turns out to be like a little 4-line equational compiler. It's very straightforward. So then when I was thinking about the consensus algorithm as trace, and then I wrote the sort of core trace idea down as a set of row terms, I realized that you could there's the same transform exists for those terms. So you can always take, so for the family of algorithms that are trace algorithms that you can write down as row calculus terms, you always have this source-to-source translation, so you can always get an economic version of it. Now, that doesn't mean that you always get slashing conditions, but it's kind of the precursor to being able to do this for an entire family of algorithms. So we have a step which says, if, and so there are a bunch of ifs, right? If we capture all consensus algorithms as a trace, and there's sort of a lot of evidence that that's reasonable. That's at least a minimal reasonable set of assertions. then and for those trace algorithms that we can represent in this fashion, then we always have an algorithm which converts them into an economic algorithm, and then you can go about turning that into a slashing condition based algorithm. So it's a stage of more, it's a sort of sequence of morphisms that under certain conditions will guarantee to get you from ordinary consensus algorithm to an economic based algorithm. So at least I have an approach to that problem now.
Vitalik, what was the situation you were describing? So
let's say that you have a checkpoint A, or let's say a checkpoint C1 with validator set A. Then after that, you have a checkpoint C2, which is a descendant of C1. And C2 transfers over from like A to B. And let's say you have another C3 that's also a descendant of C2, and then that does another switch over. So like now validators after C3, the validator set A should not be involved in anything at all. Now let's say C3 has a child C4, and that child C4 is like properly signed by the new validator set. But then you also have another child C4 prime, where C4 prime is signed by the original validator set. So if you just follow the kind of the fork choice rule as I have it implemented in my Python simulation right now, then what could happen is like you would see C1, and then you would see C4 prime that's signed by the same validator set, and it looks like it has the most signatures, and so you would jump to it, not realizing that the validator set something else in the middle.
Yeah, you have to check things in the middle. Yes.
Yes.
Okay.
Can't you? Isn't that more like a? If you have the validator sets change at fixed times, can't you just kind of look at the wall clock and figure out that there were messages missing?
So you can definitely figure out that there's messages missing because they have like epoch counters. But the point is that you have to actually explicitly go from like n to n+1 to n+2. You can't just like skip in the same way you can with a fixed validator set.
Yes, that means you have a total ordering on epochs.
Well, I mean, you always need a total ordering on epochs, but here the point is you have to actually inductively walk through the total ordering.
Cool. Well, I could give an update. First, I'll give a quick update for myself. I've been working on a number of things. I have been basically going through dependency issues with the simple Casper repo, which I need to like write about or /fix. And I wanted to fix them before I mentioned it. And then I have also been going through with Vlad his correct by construction Casper with and basically optimizing it. And third, I'm now going to be able to dedicate more time to Casper, which is exciting. Most likely, I've talked to Joe and Vitalik and Vlad, and it seems like the cards are in line for me putting in a lot more time, which is exciting. And so now for my update, that was like kind of my update, and now the update from Vlad. Vlad and I is just a little demo of what we have been working on. Vlad created this correct by construction Python simulator, and we have been optimizing it. And so we finally got to a point where it's like relatively reasonable to show. Sharing my screen. And so I'm just going to run it with 8 validators because why not? So they're basically all the weights. If you're wondering where the weights are, they're just like they increment by 1 each time. So this is the highest weight, and so you can see if you're familiar with the way that the Vlad has laid it out in his previous diagrams, The arrows represent bets that are included in the justification of the other bets. And it takes around 6. Let's see, we'll see what this one does. This is an interesting one because it goes back and forth. But it will eventually. So this one, if you see the green, means that they have reached, they've done a ideal adversary simulation, and they found that there's no possible future which it won't equal 0 in the end, which is kind of crazy. This is a little bit of a, so we have it. Oh, there we go. Nice. So we have a some slowdown, which happens at the later rounds, which we have to fix. There actually shouldn't be any kind of slowdown per round, but hopefully this one ends up pretty done. So good. So they came to consensus here. As you can see, it has some kind of crazy stuff that goes on, but yeah, that's generally it. Does that make sense?
Yeah, that's pretty cool. So my question then is, how far is the stuff that Yoichi has simulated or formally verified? How far is that from the simulation?
Okay, it's different. Okay, so yes, actually I did something with this Vlad's algorithm, and so far I haven't done, okay, I proved one theorem that says when you have a safe estimate on one set of nodes, and when you have a safe estimate on another set of nodes, when you take the union of these nodes, these are also safe. So safe estimates are these green dots. And yeah, basically I proved that these green dots stay green if you bring in other nodes not drawn in this picture. But yeah, that's the thing. But I haven't done anything about how to color these green nodes. I haven't done anything about this concrete decision procedure.
Yeah, from my understanding, they're both asynchronous binary consensus, Casper. So they should be. I think that they're pretty close. This is like the simple version.
So the protocol is the same. I mean, when a node gives a bet, it has to be the maximum weight bet. So the protocol is the same.
Cool.
Yeah, and that actually is kind of the whole point of the typing system in Rolang. So what we do is we guarantee that the code that you write is the code that is checked, which is the code that is deployed. So when our safety conditions are expressed as types in the behavioral type system, then when you write your code, it's been checked. It's been formally verified, automatically formally verified, that the code is the one that the code that you're running and deployed is the one that was proven correct. And so that's kind of that helps with keeping track of what's the relationship between the protocol that you're deploying versus the one that you're formally verifying.
Yeah, Yoshida reminds me of session types, and yeah, I wonder why isn't anybody using session types for smart contracts?
Well, that's exactly one of the things that Rolang is doing.
Okay.
Yeah.
Cool.
They're actually richer than session types. Session types is a subset of the set of types we can express.
So my update is from the last call. Okay, I had a call with Lucius, but I forgot about it, and then I was just formalizing the dynamic validator set Casper of Vitalik. So on Saturday, I released a blog post, and Vitalik saw that, and he realized a typo in slashing condition, but the proof was complete anyway, and I tried removing these slashing conditions 1 and 2. The proof still worked. That was weird. So the problem was in the statement. In the statement, I said whenever a fork happens, so some validators must be slashed. That's the statement. In the assumption, I stated there is a fork. And at that moment, I was describing a fork with branches, with prepare and prepare source, some structures. And this structure, in reality, this structure was made sure to exist by the slashing conditions, but I already assumed that structure exists, the structure, the history of prepare and prepare sources already. So I didn't need two slashing conditions. That was a problem. I fixed that over the weekend, and now it's again working. Still messy. I have to do some cleanup, and maybe I have to write some post-mortem about it.
Sweet. And this is
Yeah.
really exciting. This is super exciting to see all this progress.
Thank you.
Are there any other updates to give?
Let's see. Nothing else I can think of. I mean, there's small stuff to do with Metropolis, but that doesn't really have to do with us directly. It's more about the right way to do things like pure functions inside Ethereum. Basically, the debate was the original idea was to add in an opcode that would do like a pure call, so it can't read or write from the state. And one of the challenges that we discovered is that this is difficult to make compatible with the concept of software libraries, because software libraries would have to be part of the state. And so that they would be, you would have to be able to read them in order to use them. And the kind of resolution that I found is basically, instead of doing an opcode for pure calling, you would have an on-chain kind of checker where you could submit contracts to it, and the checker would check that the contracts actually are pure, and if it is, it would stick them in a registry. And it would have a rule that says that a contract can still be pure if it makes calls, as long as those calls go to things that are already in its registry. So I thought that was an interesting innovation. It'll also push Casper forward faster.
Oh, nice.
So Vitalik, could you just explain what Metropolis is? Because there's going to be people watching this that are new.
Sure.
Yeah.
So Metropolis is the next major hard fork that we're planning to make. So planned for release maybe 3 to 4 months from now. This is going to include a bunch of features, including some new transaction formats, in support for elliptic curve pairings, which are like a very important cryptographic primitive that once included lets us do ZK snarks on top of Ethereum. And if people new to Ethereum wants to know what ZK snarks are, I suggest they just look up the concept. It's ZK SNARK. It's basically one of the most powerful privacy technologies you can that exist out there, and like Zcash, for example, is using it.
Great, cool. I guess we can talk more about that when, obviously 3-4 months down the road. So sounds crazy. Another hard fork. Here we go. All right, that's all I had. It looks like he kind of lagged out there so I mean, we can wrap it up if you guys are done.
I think we're done. Again, productive, short, sweet, to the point, and yield back minutes to people. I think that's an awesome way to go.
Cool.
Hello. Can people hear? Are people back to being able to hear me?
Yeah, you're good.
We can hear you now.
Yeah, so basically ZK, like as I was saying before, pairings are good for ZK snarks, which are really good for privacy. It's the same technology used in Zcash. Then on top of that, it'll include some optimizations, some security improvements. Part of it is to kind of lay the groundwork for being able to for some of the things that we want to do with Casper in the future. And basically, it's like a bunch of small changes stacked on top of each other. And if there was one kind of flagship thing, I'd still probably say it would be the snarks, but like it's really probably 3 to 4 times bigger than that.
Cool. Thanks for explaining that. I just didn't. I didn't know where to read up on that. So cool.
Awesome. Are we done then?
Sure. Unless someone else has something to say.
No, I'm good.
Cool. All right, guys. Next week then.
Next week.
Cool.
See you.
Peace, peace,
Hey,
peace.
Ed, I'm gonna be about 10 minutes late, okay?
All right.
Okay.